Hi, my dears. I welcomes you for the today's session about electric field. Let's see what are the outline topics of this electric field. That is electric field intensity or electric field strength, electric field intensity due to a point charge, superposition principle, electric lines of force due to a point charge, due to a dipole, due to a equal and like charges, due to a uniform field. Properties of electric lines of force, electric dipole, electric field intensity due to an electric dipole, torque on electric dipole, work done an electric dipole. Let's see what is electric field. Electric field is a region of a space around a charge. Just you are taking a charge. Around this charge, whatever reason we have, and that will be called as the electric field. The charge which around the space which around a charge is called as the electric field, or a system of charges within which other charged particle experience. A system of charges within which other charged particle experience electrostatic force. Electrostatic force. So you can take here electrostatic force which experience two charges, as we discussed in previous session, where two charges are experienced. That might be attractive concept or it might be repulsive character, and this will be called as the electric field phenomena. Let's see here electric field definition we completed, and simply it will be called E equal to F by Q. The charge, so the ratio between force and charge will be defined as the electric field. And what are the units of electric field? F stands for Newton, Q for the Coulomb, that means Newton per Coulomb. Electric field intensity or electric field, both are same only. Electric field in strength, this is also same thing for the electric field. Electric field strength or electric field at a point in an electric field is the electrostatic force per unit volume or per unit positive charge acting on a vanishingly small positive test charge placed at the point. That means E equal to F by Q naught. From the Coulomb's concept, we already discussed what is F. F equal to K into Q1 Q2 by R square, or F equal to Q naught Q1 by R square, where K equal to 1 by 4 pi epsilon naught. This we discussed in the previous session. Now just as we discuss here, E equal to, what is the formula? E equal to F by Q. Now substitute the value of F. What is F value? 1 by 4 pi epsilon naught Q naught, and Q by R squared by Q, this Q, then Q naught. Q naught will be cancelled. Finally what you will get? E equal to 1 by 4 pi epsilon naught Q by R square into R caps, where R caps is the unit vector. Notes: if the charge is taken positive, the direction of electric field is along the direction of electrostatic force. So here the field direction, when the charge is positive, the field direction is along the electrostatic force. That means force and electric field both are in same direction if you are taking the charge is in a positive manner. If the charge is taken in a negative manner, that means the direction of E is opposite to the applied force. Opposite to the applied force. In case 1, where you are taking the positive character, the charge is a positive charge, that means F and E both are in same direction. Both are in same direction. If the charge is negative, F and E both are in opposite direction. Both are in opposite direction. Electric field is a vector quantity. Electric field is what? It is a vector quantity. Then what are the units of the electric field? As we discussed previously, electric field definition is Newton per Coulomb. Then electric field due to a point charge. Electric field due to a point charge. Let us consider these two figures. Then you can see X, Y, Z and origin O. At the point is P. At the point P, the charge is Q naught. At the origin, the charge is Q. Now upon this point Q naught, a force F is working. Now we need to find this F value at this point. Let's see, from the Coulomb's law or vector formation, we can analyze, that is vector law of Coulomb, that is 1 by 4 pi epsilon naught into Q naught by R square into R caps. From the electric field definition or electric field strength definition, E equal to F by Q naught. E equal to F by Q naught. Now replace this value, then what you are getting, that means E equal to F value is what? F is what? 1 by 4 pi epsilon naught Q and Q naught by R square. So Q naught will be cancelled, and finally E equal to 1 by 4 pi epsilon naught Q by R square into R caps. The electric field due to a point charge as spherical symmetry. What is the shape of that one? You can see the due to a point charge, the shape of the electric field is what? It is a spherical symmetry. You can see here, this is about the spherical symmetry. If you plot a graph between E and R square, then it is indicating what? It is indicating electric field lines of force. It is indicating spherical symmetry. Now electric field lines of force. Next outline. An electric line of force is an imaginary straight or curved path along which a unit positive charge is supposed to move in an electric field. In an electric field, a electrical line of force is what? It is a imaginary concept. It is a imaginary. An electric line of electric force is an imaginary straightway or curved path along which a unit positive charge is supposed to move in an electric field is called as a electric field line. Electric lines of force do not physically exist. Why? Because they are the imaginary. Yes, they are not physically exist. They are the imaginary concepts. So this is about the imaginary concept of the electric lines of force. And let's see, electric lines of force due to a point charge. What is that one? Due to a point charge can be considered here. You can observe here left side figure and right side figure. So here, if the charge is greater than 0, if the charge is less than 0, then what is happening? You can see in figure A, that means a representation of electric field in terms of field vector. The size of the arrow represents the strength of the electric field. The size of the arrow, if the arrow is more size, then the electric strength is the strength of the electric field is more. The size of the arrow represent strength of the electric field. You can see here in figure B, a representation of electric field in terms of field lines. So here in the left side figure, the charges are moving from the center, and the right side figure, the charges are moving toward the center, and they're moving away from the center. You can see if the charge is less than 0, it is moving away from moving toward the center. If the charge is greater than 0, it is moving away from the center. Greater than 0 means moving away from the center. Less than 0 means moving toward the center, the field lines. Then electric lines of, these are the property, electric lines of force due to a pair of equal and unlike charges. Because of pair of equal and unlike charges, what is happening? So you can see the charges are unlike. That means one is a positive charge, the other one is a negative one. One is a positive charge and the another one is a negative charge. That means positive charge as well as the negative charge. So this is about the positive charge, this is about the negative charge. Now in this case, what we will identify, we can analyze in this case, that is electric lines of force contract lengthwise to represent attraction between two unlike charges. Electric lines of force contract lengthwise to represent attraction between two unlike charges. Then coming to the third property, electric lines of force due to a pair of equal and like charges. Equal and like charges. Here is what? Unlike. Here is what? Unlike. This is about the unlike. This is about the like, unlike, and this is about the like charges. Now let's see here. In like charges, as we know that one, like charges will be repel. Now from this figure we can analyze that electric lines of force exact lateral, that means sideways pressure, to represent repulsion between two like charges. Coming to fourth property, electric lines of force due to uniform field. Due to uniform field, you can find that one, the electric field lines of force are maintaining same positions and they are having certain position levels. So now a few more properties apart from that. The electric field lines are electric lines of force. That means, as we discussed previously also, that is electric lines of force are imaginary lines. Electric lines of force are the imaginary lines. Why they are not physically exist? A unit positive charge is placed in electric field tends to follow a path along the field line if it is free to do so. So here, if you are placing any unity positive charge in a free path, the line will be follow a straight path. Third one, the electric lines of force originate from positive charge and terminate at negative charge. So here the field of line starts from the field of line starts from the positive charge and end at the negative. Here it is a positive charge, it will be start, and negative charge, it will be end. Coming to the fourth property, the tangent to an electric field line at any point gives the direction of the electric field at the point. You can see this figure. This we have a practical also. So here the tangent to an electric field line at any point gives the direction of electric field at the point. Fifth one, two electric lines of force can never cross each other. Two electric lines of force can never cross each other. Then coming to sixth one, you can see here the two lines of the electric force not connect together. They are not interacting together. That's why it is showing that one not possible. Coming to the sixth one, electric lines of force are closer where the electric field is stronger. If the electric field is so strong, that means the lines of force are closer. If the electric field is weaker, the lines of the field is spread. So closer means it will be strong field. Weak means the field lines are spreading. Coming to seventh one, you can see the figure also here. If the field is very strong, this will be the field lines are closing. If the field is weak, then this is a spreading nature. Coming to seventh one, electric lines of force are perpendicular to the surface of positively or negatively charged body. So here the lines of electric are perpendicular to the positive charge or negative charge. You can see here positive charge or negative charge. Coming to the next one is about the eighth one. Electric lines of force contract lengthwise to represent attraction between the two unlike charges. Coming to ninth one, electric lines of force exert lateral pressure. This already we discussed previously. So if the like charges, it will be laterally spread. Coming to the 10th, so these are so coming to the 10th one, the number of lines per unit cross-sectional area perpendicular to the field line. The number of lines per unit cross-sectional area perpendicular to the field lines. Perpendicular to the field lines. So that's why E is proportional to del n by delta A, where delta n is the number of lines, delta A is the area, cross-sectional area. Coming to 11th one, electric lines of force do not pass through the conductor. Electric lines of force do not pass through a conductor. Hence, the interior of the conductor is free from the influence of electric field. Electric field lines of force do not pass through a conductor. Hence, the interior of the conductor is free from the influence of the electric field. You can see from the figure. And the 12th one is about electric lines of force can pass through an insulator. So the field lines can pass through an insulator. And coming to the next outline is about the electric dipole. Electric dipole is a pair of equal and opposite charges. Equal and opposite charges separated by a very small distance. Electric dipole is a pair of equal and opposite charges separated by a very small distance. The dielectric field produced by a dipole is known as dipole field. The electric field produced by a dipole is known as dipole field. Electric dipole moment is a vector quantity used to measure the strength of an electric dipole. Used to measure the strength of an electric dipole. So you can see the figure. See here from the figure, this is about the negative charge and this is about the positive charge. The positive and negative charges both are separated by very small distance, and this will be called as the dipole. What is that one? This will be called as dipole. Here what is small length? The small length is 2L, then 2L into this charge will be called as the dipole, that will be represented by symbol P. P equal to Q into 2L, where 2L is the distance between two charges of positive and negative. You can see here equal and opposite charges are separated by very small distance. So here, what are the units of the dipole moment? As we discussed here, that means Q into 2L, where Q is the charge, 2L means, L means what? Meter. That means Coulomb meter is the unit of the dipole. Electric field intensity due to an electric dipole. Let's see here, the electric dipole we need to consider in two ways. One is in axial and one is equatorial line. So at the axial line, this will be called as the axial line and this will be called as the equatorial line. So now your topic outline is about what? Electric field intensity due to an electric dipole. Let's see, we are taking axial path, that means axial line. At a point on the axial line, the resultant electric field intensity at the point P is the resultant electric field intensity at the point is considered as, at the point P is considered as what? That is, at this point it will be considered as EA, electric field at A, electric field at B. So EA, that will be considered, you can see here, this is EA and EB from this one, from this area. From here it will be EA, from there it will be EB. So the electric dipole at the axial path, it will be considered as EP equal to EA plus EB. Now the vectors of EA and EB are collinear and opposite. Then you can say EP equal to, that means they are in opposite, that's why we taken that one. See, one is this, one is left side, one is the right side, you can see the figure here, and one is, so here you can see one is goes to this side and this goes to this side, that means both are in opposite direction. Then we can consider they are in opposite. So EP equal to EB minus EA. But we know that from the Coulomb's, from the electric field definition, E equal to F by Q. Is it right? E equal to F by Q. From this concept, we can analyze here at point A. At what? At point A, that is EA. At point B, that is EB. The fields are EA, EB. So here EA is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught Q by. So what is the distance here? The distance here from here to here, it will be L. From here to here, it will be L. From here to here, it will be X. So that's why in the place of R, we can take as X plus L. So R square means X plus L square. Now here EA is 1 by 4 pi epsilon naught Q by X plus L all square into vector form into vector form L caps. Coming to the EB, so that will be, so here that will be 1 by 4 pi epsilon naught. Then another charge Q by C, you can take here at the point, that means X minus L. What is that one? X minus L. Then X minus 1 by 4 pi epsilon naught Q by X minus L all square into that is vector I caps. Vector in the direction of horizontal, we taking I caps. Now it will be considered as what? Then AB minus EA equal to what? After simplification, it will be considered 1 by 4 pi epsilon is the common, and Q by X minus 1, X minus L square minus Q by X plus L all square. Now after simplification, it will be considered as this value, that is 1 by 4 pi epsilon naught 2 into Q into 2L into X by X square minus L square into X square minus L square of all square, and which will be considered as the 1 by 4 pi epsilon naught 2px by x square minus L square of all square. So this is about the, so as we know that one, Q into 2L is what? Q into 2L is P. Q into 2L is what? P. Then 2px by x square minus L square of all square. Therefore, EP is what? 1 by 4 pi epsilon naught 2px x square minus L square of all square. If the value of L is less than to x, that means if the L is negligible, then AP equal to 2p pi 4 pi epsilon naught x cube, 2p by 4 pi epsilon naught into x cube. The direction of electric field intensity at any point, at a point on the axial line due to the dipole is always along the direction of dipole moment. So here the field intensity is along the dipole moment. Condition 2. At a point on the equatorial line, the resultant electric field intensity at point Q. Previously it will be P, now it will be Q. That means EQ equal to EA plus EB, vectors of EA and EB acting at an angle 2 theta, acting at an angle of 2 theta, that means EA equal to 1 by 4 pi epsilon naught q by x square plus L square. EB is what? 1 by 4 pi epsilon naught q by x square plus L square into I caps, that means I vector. The vectors E sin theta, ES sin theta, AB sin theta are in opposite and each other, opposite to each other. That's why the two signs of EA sin theta and EB sin theta will be cancelled. Why? Because they are in opposite in nature. Therefore, the vectors EA cos theta, EB cos theta are acting along the same direction. Hence, they are arriving. So, sines angles are cancelling because of the opposite character. So in the place of sine, we are considering another one, that is another remaining two angles we are considering from the geometrical structure. So that is EA cos theta, AB cos theta for the EQ. Now this above figure we can consider, that is EA and EB is what? So EA cos theta will be considered. So the summation of the EA cos theta plus EB cos theta will be considered 2 by 4 pi epsilon naught q by x square plus L square into L by x square plus L square of over 1 by 2. After simplification, it will be EQ equal to 1 by 4 pi epsilon naught q into 2L by x square plus L square over 3 by 2. We know that 1 q into 2L is a p. Therefore, EQ equal to 1 by 4 pi epsilon naught into p by x square plus L square over 3 by 2. So here, as we know that one, if L is less than y, then we simply replace the x is going to be replaced by y, then it will be eq equal to p by 4 pi epsilon naught y cube. So here L will be cancelled, that means you will get the x value, the x is less than to the L and L is less than to, sorry, the x is greater than to the L. Similarly, y is greater than to L. This is we are considered condition in the place of x. We are taking y. Then y is greater than to the 1. So that's why AQ equal to P by 4 pi epsilon naught y cube. And finally, we can analyze that one. The equatorial point dipole is greater than to the, sorry, the equatorial dipole is less than to the axial dipole. So here that means your equatorial dipole is what? P by 4 pi epsilon naught y cube, but axial dipole is what? 2 times of the equatorial. 2 times of equatorial. So that's the reason we are taking that one. The dipole moment along the axial is more greater than the equatorial line. And coming to the another outline, that is torque on an electric dipole in uniform electric field. Let's see the force of magnetic field. So the force of magnitude PE acts opposite to each other, and hence net force acting on the dipole due to the actional uniform electric field is zero. So therefore no translation motions of the dipole. However, the force are along the different lines of action and constitutes a couple. Hence the dipole will be rotate and experience a torque. Therefore torque equal to electric force into perpendicular distance. That means torque tau equal to q into e into 2l sin theta. As we know that one, 2l into q is what? P. So 2l into q is what? P. Then pe sin theta. Therefore torque tau equal to p into e. That means dielectric of torque is, or direction of the torque is perpendicular to the direction of torque is perpendicular to the perpendicular into the plane of the containing P and E. Therefore, the torque is units are what? The torque units are Newton meter. Then work done on an electric dipole in uniform electric field. When an electric dipole is placed at a uniform electric field, it experiences torque and tends to align such a way to attain the stable equilibrium. To get the stable equilibrium, it is tending, and that will be become as a work done in electric dipole, and that will be considered as the dw equal to tau into theta, tau into d theta, tau into d theta. Therefore, dw equal to tau means what? Previously we discussed tau equal to pe sin theta. Tau equal to what? Pe sin theta. Now replace here w equal to the integration from theta 1 to theta, that is pe sin theta d theta, where theta 1 is the lower one and higher one, theta 2 is the higher one. Therefore, w equal pe cos theta 1 minus cos theta 2. If the potential is energy is arbitrarily taken 0 when the dipole is at 90 degrees, then potential energy rotating the dipole and incline it an angle theta. Therefore, potential energy is considered as a minus p cos theta, minus P cos theta. Therefore, potential energy can be taken 0 arbitrarily at any position of the dipole. At any position of the dipole. Thank you.